In this lecture, we are going to continue the examples in the exercise 6.2. Okay. The example number 1 we have already done in the last 2 lectures. Now the example number 2. Here in this exercise we see the examples of the formation of the differential equation. That means form the differential equation. Differential equation, it is an equation which contains the derivative of the functions. That means here given an equation, we differentiate that equation and find the differential equation. Okay. In the previous lectures there is a equation is already given, but in this lecture we see the examples where the equation is not given. First we find the equation, okay, from using the condition in the examples. Now here the form the differential equation of family of lines having intercept a and b on the coordinate axis. That means equation of line in a double intercept form. It is x upon a plus y upon b is equal to 1. In the last lecture we see the examples. There is a equation is already given. We only differentiate and removing the arbitrary constant and find the differential equation. Now first here we first write the equation, identify the arbitrary constants and then differentiate. Okay. Now here form the differential equation of family of lines having intercept a and b on the coordinate axis. Here we know that the equation, okay, here the equation of lines, equation of a family of lines having intercepts a and b on the coordinate axis is, we know the equation, it is x upon a plus y upon b is equal to 1. Okay. Now here a and b are the arbitrary constant. Here a and b are the arbitrary constant. That means there are the two arbitrary constants. So here differentiate twice. Okay. Here first differentiate with respect to x. Differentiate with respect to x. Here x upon a. Here 1 by a is a constant. 1 by a is a constant. And derivative of x it is 1. Plus 1 by b is a constant and derivative of y it is a dy by dx. And here it is a 0. It is a derivative of 1. Now we can write 1 by b dy by dx is equal to minus 1 by a, and therefore dy by dx is equal to minus b by a. Again differentiate. With respect to x, therefore d2i by dx2 is equal to 0. Derivative of dy by dx it is d2i by dx2 and derivative of minus b by a it is a 0. Here is a required differential equation. Here it is a differential equation of family of lines having intercept a and b on the coordinate axis. It is d2i by dx2 is equal to 0. Okay. Now we see the next example. Here example number 3, find the differential equation of all parabolas having length of lattice rectum length of lattice rectum 4a and axis is parallel to the x-axis. Okay. Now here axis is a parallel to the x-axis. That means it is not a standard parabola. Okay. Axis is parallel to x-axis. Okay. Here, and the length of lattice rectum, it is a fixed. It is a 4a. Here it is a general parabola. Okay. Here, given that the length of lattice rectum, here given that the length of lattice rectum is 4a, it is given. Okay, let it is, and given it is a axis is a parallel to the x-axis, and axis is parallel to x-axis. Okay, now let it is h comma k is vertex. Okay, now see carefully. Axis is a parallel to the x-axis. Okay, that means our parabola becomes here. It is x-axis, it is y-axis. Axis is a parallel to the x-axis. We can draw here, here, or here. Here, the axis of the parabola is this. Okay, it is a parallel to the x-axis, and vertex it is h comma k. Okay, and the length of lattice rectum, it is a given. It is a 4a length of lattice rectum. Okay, it is a parabola. It is origin. It is y-axis. It is x-axis. It is vertex. And it is the axis of the parabola. Okay, and here it is a focus. Yes. Okay, axis is a parallel to the x-axis. Axis is parallel to the x-axis. Now the equation of parabola, therefore equation of parabola is y minus k whole square is equal to 4a into x minus h. Okay, here it is an equation of the general parabola. Here the length of lattice rectum is given. Therefore here only the h and k are the arbitrary constant. 4a is not an arbitrary constant. Here a is not arbitrary constant, because here given that the length of lattice rectum is fixed 4a and axis is parallel to the x-axis. Okay, therefore here it is the equation of parabola. Now there are the two arbitrary constant. Here h and k are arbitrary constants. Okay, therefore we differentiate this equation twice. Okay, then differentiate with respect to x. It is y minus k whole square. Y minus k whole square, it is 2 into y minus k into dy by dx. It is a derivative of y minus k whole square. It is a 2 into y minus k into dy by dx. Now here 4a, it is a constant, and derivative of this, it is 1 minus 0. That means here it is only 4a. It is a derivative. Therefore this 2 to get cancelled, we can write y minus k dy by dx is equal to 2a. Okay, here it is a first derivative. Now again differentiate. With respect to x. Now here y minus k into dy by dx. Here we use the u into v, and it is a 2a constant. Here 0 derivative. Differentiate with respect to x. First function as it is, that is y minus k into d2i by dx2, plus second function as it is, dy by dx into derivative of this y minus k, and derivative of y minus k, it is a dy by dx is equal to 0. See carefully this. Now here the k is an arbitrary constant is remaining. Now remove this arbitrary constant. Therefore here it is equation number 1. Here it is a y minus k, and then y minus k is equal to 2a upon dy by dx. Therefore y minus k, it is 2a upon dy by dx into d2i by dx2 plus dy by dx whole square. It is a dy by dx whole square, it is d2i by dx2, and this y minus k, it is a 2a upon dy by dx by 1. Here it is by 1. Now it is dy by dx, again multiply, so it is equal to 0. Okay, now multiply by dy by dx. Therefore we get 2a into d2i by dx2 plus dy by dx whole cube dy by dx. Okay, multiply by dy by dx is equal to 0. Is a required differential equation. Okay, here it is a required differential equation. It is a equation of parabola having vertex at h comma k and length of lattice rectum, it is a 4a. It is a equation of parabola, and then we differentiate twice. Here h and k are the arbitrary constant. Length of lattice rectum is given, it is fixed. Okay, it is 4a. Therefore h and k are the arbitrary constant. These two arbitrary constants eliminate from this equation, we get the differential equation. Okay, now the next fourth example. Example number 4. Find the differential equation of an ellipse. Differential equation of an ellipse whose major axis is twice its minor axis. Now here we know the equation of ellipse. First we can write the equation of ellipse. Equation of ellipse, it is x square upon a square plus y square upon b square is equal to 1. Okay, here it is the equation of ellipse. X square upon a square plus y square upon b square is equal to 1. Therefore the major axis and the minor axis, length of major axis it is a 2a and length of minor axis it is a 2b, and here the given condition, length of major axis is twice the length of minor axis. Here given that length of major axis is twice the length of minor axis. Okay, therefore we can write length of major axis it is a 2a and 2 into length of minor axis it is a 2b. Okay, see carefully this 2 get cancelled, therefore we get a is equal to 2b. Okay, here a is equal to 2b, put this value in the equation of ellipse. Therefore equation of ellipse becomes x square upon a it is a 2b, therefore here it is a square, therefore we can write 4b square plus y square upon b square is equal to 1. And now in this equation there is only one arbitrary constant, it is a b. Okay, therefore here we take this b square common. Now here we take the 4b square, 1 by 4b square common. Here 1 by 4b square. Then here it is a x square plus 4y square is equal to 1. Then x square plus 4y square is equal to 4b square. And now differentiate. Differentiate with respect to x. Then we get the derivative of x square, it is a 2x plus derivative of 4y square, it is a 4 as it is, and derivative of y square, it is a 2y dy by dx, and is equal to 0. The 4b square, derivative of 4b square, it is 0. Now here we take 2 common, therefore x plus 4y dy by dx is equal to 0 is our required differential equation. Here the condition is length of major axis is twice the length of minor axis. That means 2a is equal to 2 into 2b. 2a is the length of major axis and 2b is the length of minor axis. We get the relation, put the value of a. Therefore here only one arbitrary constant here. B is arbitrary constant. B is a arbitrary constant. Okay. Now, this is the next example, fifth example. The example number 5. From the differential equation, of family of lines parallel to the line 2x plus 3y plus 4 is equal to 0. Now here first we want to find the equation of line parallel to this line. Here given line it is 2x plus 3y plus 4 is equal to 0. It is given line. We want to find the equation of line parallel to this line. Here it is a equation of a straight line. Two lines are the parallel, that means the slope of two lines are the same. That means here the slope of this line, it is a minus 2 by 3. Therefore slope of the parallel line, it is again minus 2 by 3. That means the coefficient of x and y are the same of the two parallel lines. Only difference between the constant. The equation of line ax plus by plus c. Okay, a and b are the same. Only difference between in the constant c. Okay, these are the two parallel lines. Therefore the equation of line parallel to given line here it is 2x plus 3y plus c is equal to 0. Here c is arbitrary constant. Okay. Then differentiate this equation. Differentiate with respect to x. Derivative of 2x, it is 2, plus derivative of 3y, it is a 3 into dy by dx, and derivative of this constant, it is a 0, is equal to 0, and therefore 2 plus 3 dy by dx is equal to 0 is required differential equation. Okay, it's a simple question asked to the 2 marks or 1 marks also. It is a 2x plus 3y plus c is a family of all lines which are parallel to this line. Okay, here c is arbitrary constant, takes any real value. Okay, then these are the infinite lines which are the parallel to this line. Okay. Now the next example. Form the differential equation of all circles having radius 9 and center at point h comma k. Here we know that the equation of circle having center and radius, it is x minus h whole square plus y minus k whole square is equal to r square. R, it is a radius 9, it is given. That means there are the two arbitrary constants h and k. Okay. Therefore equation of circle having radius 9 and center at h comma k is here x minus h whole square plus y minus k whole square is equal to 9 square. Okay, here it is the equation of circle. Okay, now here h and k are arbitrary constants. Okay, that means there are the two arbitrary constants. Differentiate this equation twice. Okay, here first differentiate with respect to x. Okay, here the derivative, it is a 2 into x minus h, 2 into x minus h plus 2 into y minus k into dy by dx. Okay, see carefully the derivative. Here it is x minus h square. We use the standard formula for the x square. Derivative of the x square, it is a 2x, and then derivative of the x minus h, it is 1. Here derivative of x square, it is a 2x, but here x replaced by the y minus k. So the derivative of y minus k, it is a dy by dx, and derivative of this 9 square, it is a 0. Okay. Then 2 take a common, then we get x minus h plus y minus k dy by dx is equal to 0. See carefully this. Now again differentiate. With respect to x, then x derivative of x minus h, derivative of x, it is 1 and it is a 0. Okay, plus y minus k into dy by dx. Here we use the u into v. first as it is, y minus k into derivative of the second function, that is a d2y by dx2, plus second as it is into derivative of the first, that is a dy by dx, is equal to 0. Okay, now here this is the original equation. We differentiate this equation, we get this. Here we take the equation number 2. Now again differentiate this, we get it is a 1 minus 0 plus 1, it is a derivative of x, 0 it is a derivative of h. Then y minus k into dy by dx. Here we use the u into v, first as it is, derivative of second, plus second as it is and derivative of the first, that is derivative of y minus k. Derivative of y, it is a dy by dx, and derivative of k, it is a 0. Now here we can write it is a 1 plus y minus k into d2y by dx2 plus dy by dx square is equal to 0. Now we want to find the differential equation by eliminating the arbitrary constant h and k. Okay, here it is first derivative and it is second derivative, but here h and k not remove. Okay, therefore here find the value of this y minus k and it is x minus h from both two equations. Okay, here we take it is equation number 2, sorry it is equation number 3, it is equation number 2. By equation number 1, sorry, by equation number 2, by 2 we get here x minus h is equal to minus y minus k into dy by dx. Okay, here x minus h is equal to, we take the RHS, it is minus y minus k dy by dx here. Now this x minus h and by equation number 3 we get here it is a y minus k, see carefully, y minus k d2y by dx2 is equal to minus 1 minus dy by dx whole square. Therefore y minus k is equal to, here d2y by dx2 take in the division, here it is minus minus, we take minus common, then we can write 1 plus it is a dy by dx square and whole to the upon d2y by dx2. Now it is x minus h and it is y minus k. Put the values in this x minus h whole square plus y minus k whole square is equal to 9 square, that is the equation number 1. Okay, here we put the value one by one. Okay, put x minus h in, it is x minus h in equation number 1. Therefore we get x minus h, it is a minus y minus k into dy by dx whole square plus y minus k whole square is equal to 9 square. Here it is the equation number 1. Only we put the value of the x minus h and then it is y minus k whole square dy by dx square, it is a square of this term, plus y minus k whole square is equal to 81. Okay, again take the y minus k whole square common, y minus k whole square into it is dy by dx whole square plus 1 is equal to 81. Okay, now we put the value of x minus h in the equation number 1, we get this equation. Therefore the y minus k square, it is a y minus k, value of the y minus k. Okay, one more step we can draw right here, it is dy by dx whole square plus 1 is this, is equal to 81 upon y minus k whole square. Here this y minus k whole square we can write here, and now here y minus k is this, and here 1 by y minus k. So this is a numerator and this numerator we can write in the denominator. Therefore here 81 into d2y by dx2 square and whole to the upon this term minus 1 plus square. Okay, here we can write in the bracket, square bracket. See carefully this calculation. Here it is a y minus k square, and y minus k is this d2y by dx2 we can write in the numerator, and here it is a minus 1 plus dy by dx square. It is a minus 1 plus dy by dx whole square, and here square because it is a y minus k square. Okay, it is a dy by dx square and it is a whole square. Now then it is dy by dx square plus 1, this is equal to this 81 d2y by dx2 square, and now here it is a minus and this square we can directly write it is dy by dx square plus 1 whole square. See carefully, it is 1 plus dy by dx square, it is 1 plus dy by dx whole square, it is a minus we can write directly whole square. Now this dy by dx square plus 1, it is dy by dx square plus 1, it is a square we can write in this. Therefore our last answer, it is dy by dx square, it is a dy by dx square plus 1 whole cube is equal to, here dy by dx square plus 1, dy by dx whole square plus 1, but here it is a dy by dx square plus 1 square. We take the multiplication, it is whole cube is equal to 81 d2y by dx2 square. Okay. Here it is 81 d2y by dx2 whole square, it is d2y by dx2 whole square, and here it is our required differential equation, dy by dx square plus 1 whole cube is equal to 81 d2y by dx2 whole square. Okay, see carefully the calculation. First it is a equation of circle, then it is a first derivative and it is a second derivative. Okay, here from the equation number 2, from the first derivative we find the value of x minus h, from the second derivative we find the value of y minus k, and these two values put in the equation number 1 we get this equation. Okay, see carefully this. Check all calculations carefully. Okay. Now the last example in this exercise. Example number 7, form the differential equation of all parabolas whose axis is the x-axis. Okay. Here we want to find the differential equation of all parabolas whose axis is the x-axis. Here axis is the x-axis, but Here the vertex is not origin. Okay, here vertex, the position of the vertex is not given, so the position of vertex is anywhere, at origin also or on the x-axis. Okay, at any point. Okay, we know the equation of the parabola. Okay, axis has a x-axis. Okay, here the general parabola y minus k whole square is equal to 4a into x minus h. Okay, y square is equal to 4ax, but here vertex is not origin, therefore h comma k, but axis as a x-axis, therefore vertex on the x-axis, therefore on the x-axis there is a y coordinate is 0, that means this y coordinate is 0, therefore our equation is y square is equal to 4a into x minus h. Here the two arbitrary constant a and h. Okay, in our previous example in this lecture here of the parabola, okay, there is a length of lattice rectum is given, so there is, we cannot take 4a is an arbitrary constant, but here the length of lattice rectum or any point is not given. Here 4a is, a is also arbitrary constant and h is also arbitrary constant. Okay. Now here let the equation of parabola, we can write the equation of parabola. Equation of parabola whose axis is the x-axis, that is vertex on x-axis. Okay, then let it is h comma 0 is vertex. Okay, now our parabola becomes here, it is x-axis, y-axis. Here vertex of the parabola on the x-axis at any point, origin also. Okay, at any point. Okay, we take here it is h comma 0. Okay, it is a vertex. Now therefore the equation of parabola is y minus 0 whole square is equal to 4a into x minus h. Okay, now therefore you can write y square is equal to 4ax minus 4ah. Okay, it is the equation of parabola. Here a and h are arbitrary constant. Okay, therefore differentiate with respect to x. Okay, we differentiate twice because there are the two arbitrary constants. Here first derivative is 2y dy by dx. It is a derivative of y square is equal to 4a minus 0. 4a constant as it is, derivative of x is 1, and it is 4ah, it is a constant, therefore derivative is 0, and therefore it is y dy by dx is equal to 2a. Okay, it is the first derivative. Now we take the second derivative, that is differentiate again differentiate with respect to x. Differentiate with respect to x. Here first function as it is, derivative of the second function plus second as it is, derivative of the first is equal to 0. Again here we use the u into v, y into dy by dx, differentiate with respect to x. First as it is, derivative of second, plus second as it is, derivative of first, and derivative of 2a, it is a 0. Then the last answer it is y d2y by dx2 plus dy by dx whole square is equal to 0 is our required differential equation. Okay, see carefully. This equation of parabola whose axis has a x-axis and vertex on the x-axis on the at any point. Okay, therefore the equation y minus 0 whole square is equal to 4a into x minus h. It is the equation of parabola. Then a and h are the arbitrary constant, so we differentiate twice and we get this differential equation.